Hello everyone. In this module, we are going to learn about linear algebra and cover different areas in linear algebra that are very much essential for us to learn or progress further towards machine learning, deep learning, and other unsupervised learning algorithms and recommender systems, of course. So before we get into linear algebra, let's understand that linear algebra as a mathematical area has got wide spectrum of applications in machine learning and deep learning. And I do not want to get you introduced to all those terminologies and nuances or probably the techniques that linear algebra finds its applications and confuse you, right? That's not my objective here. My objective is to take a step by step approach and then get you introduced to all the essential mathematics or get you introduced to all the essential concepts of linear algebra, which forms the foundation for machine learning and deep learning agenda. All right. So to begin with, I would want to make you aware of how you represent the data. Of course, you are trying to solve a specific problem using ML or AI models, isn't it? That's the objective here. You will be given with some sort of source data. You might be given the data in the form of images, you might be given the data in the form of text, or you might be given user preference data or some structured data, right? Structured data is the data that you'll be most often given with. The user preference data is pertinent to input data for the recommender systems. Let's say you have access to Amazon or Netflix data here, and probably thousands of users would have interacted with thousands of different movies as such, and they also would have rated hundreds of movies and all. Obviously, all of that data is called as user preference data because every single user will have his own taste or preference depending upon various attributes that he has. And you represent this particular data in some form. Text data also you represent in some form, and image also you represent in some form. In some form that the computers can understand. The computers cannot understand image data or it cannot understand text data. Right? It always understands the numeric data, that is numbers. You convert this image into a matrix with different numbers. So each pixel would actually denote a particular vector or number, whatever you are representing, by considering the grayscale. Right? Grayscale actually ranges from 0 to 255. Let's understand how you represent every pixel in the form of a value that ranges in between 0 to 255 much later when we discuss about deep learning. But the essential thing that we are gaining from this discussion is that every single source data can be represented in terms of numbers here. The text data also can be represented in terms of something called TF-IDF matrix, which essentially has got numeric data represented in the form of a matrix. I don't want to get into all these details now. All right. Or geometrically, you can represent all this data or organize this information into a vector. There is something called as a vector that's available in a vector space where you can represent all your data points or where you can represent all your observations. If it's causing confusion, that's totally fine. But let's understand what a vector is first and then go into further discussion. A vector is nothing but it's a mathematical object which basically has got both magnitude and direction. It can also be treated as a one-dimensional array of numbers. For instance, this is the, let me go a little further and then let's come back to the slides again. So this is the data that's given to us. This is an example, right? So this is an example that we are considering. So this data essentially has got different features like age, income, and credit rating. There is another feature called response feature or target feature, which we are trying to estimate. Our objective is to estimate whether a new customer or whether a particular new loan applicant to the bank, whether he is going to default or not default, depending on the historical data that we have. All of this is historical data. In machine learning, when we construct ML models, we rely upon historical data a lot because that's when you understand what the true values are. So this is the estimate that you are trying to assess, and you already have recorded most of the data historically so that any new entry that comes today, that is in real time, you will have values for age. Suppose a new customer has got an age of 37, an income of 62,000, and probably a credit rating of 91. Since you already have a mathematical model that you have constructed depending upon the different historical data that you have, you will be able to estimate this value because this is going to occur in future, right? So we will get to know only that this particular new customer is going to default or not default only in the future. all these records that you are observing here, has occurred in the past. And hence we have all these values that are recorded. So you create a mathematical model, that is create a function called f of x, which would estimate your loan default, which is given by y here, and whatever equation that you come up with, that will help you in deducing or estimating whether a particular customer can default a loan or not. Or geometrically, you can represent every single feature that you have here. So this is your feature, this is your feature 1, this is your feature 2, and this is your feature 3. And this is your target. So every single feature, that is age, can be represented as a dimension in a vector space. So this is your vector space. Let's call it as a vector space, or probably you can call it as a coordinate space. And you also have another feature, that is feature 2, called income. Another feature called credit rating. And every single observation will be a point or a vector, depending on what values that these particular observation has got for age, income, and credit rating. Age is 24 points away from origin, and income is like probably 10,000 points away from origin. And of course, credit rating is like 98 points away from origin. There will be various other vectors that are possible in this vector space. Every single vector here, that is v1, v2, v3, v4, or whatever, right? All of this are your observations. So your observation 1 is pertinent to vector v1, and you can see the data here. Your observation 2 is pertinent to vector v2, and so on. So every single observation now can be represented as a vector in your vector space or in your coordinate space, where your features are nothing but dimensions. So you have represented your features as dimensions here. So this is your feature 1, feature 2, and feature 3. So these are the different vectors that we were talking about, or these are the different observations that we are talking about, depending on the values that these particular observations has got. And this is how you can geometrically interpret the data that you have, or geometrically represent the data that you have. You can represent the data in the form of vectors. And that's what I was saying here. So vector is a one-dimensional array, and that's what we have learned about. So your one-dimensional array was like 24, 10,000, and 98, isn't it? This is your column vector. This is pertinent to your observation 1. And of course, this 24 is pertinent to your feature 1, that is age. This 10,000 is pertinent to your income feature, that is feature 2, and 98 is pertinent to credit score, that is feature 3, right? And you have represented that in a 3-dimensional vector space. And all of them are real values in 3-dimensional vector space. And it could yield into n-dimensional vector space also when you have n number of dimensions. There are possible scenarios where you have n number of features in your data, isn't it? You cannot always expect the data to be in the form of 3 different features or 2 different features for simplicity, right? In real world scenarios, you will have thousands of different features where you might end up considering a confined set of features for your final model. Even that confined set of features will be in hundreds sometimes, right? Of course, those confined set of features could be represented as n-dimensional vector space depending on the value of n there. If you are finalizing 232 different features, and probably you have 232 dimensions in your vector space. And that's what we are talking about. So you are representing your observations as data points or vectors within this particular coordinate space that you have. I believe you have pretty much understood about what a vector is and how you represent a vector, or how you represent each observation that you have within the data in the form of a vector, isn't it? And this is what we're talking about, right? So you have this particular vector called v1, which is associated with observation 1. So 24 is nothing but your feature 1 age, 10,000 is nothing but your income, and 98 is nothing but your feature 3, that's credit rating. Likewise, every single observation will have a different vector altogether till you exhaust all the observations that you have in your data. All right, perfect. So what are the different examples that we have discussed earlier? So we have discussed about the image data, words or documents, that is text data. We have also discussed about user item matrix, that is nothing but user preferences data. apart from the structured data that we have seen in the previous example, right? All of these data representations are very sparse. Imagine that you have a very large document, right, where you have tens of thousands of words. Then obviously, whatever data, that columns that you have will be nothing but your words. That is word 1, word 2, word 3, word 4, or word 5, and so on, right? And this could be your document 1, this could be your document 2, and so on till document n, right? There are n different documents that you have. Of course, when you have tens of thousands of different columns, then obviously your data is very sparse, isn't it? Or let's consider a much familiar example, that is the Netflix data, where your rows are nothing but users. That is every individual users like us, right? Of course, we have thousands of movies. Every single column here is a movie. And not every single user will watch all the movies that we have. He only rarely watches about 100 of them at max, right? So you have more than 10,000 different movies here. Of course, all the data will be 0, 0, 0, 0, except for few movies that he has watched, right? Or probably if this is a rating matrix, then probably you'll have the rating values associated with the movies that he has rated. There could be some movies that he has watched but not rated, isn't it? So this kind of data is very sparse because you find large number of values within this matrix to be zeros and does not hold any information at all, right? All such kind of data representations are very sparse, and linear algebra helps us provide certain tools in extracting only the relevant portion of the data from the ambient large dimensional vector space that we have. In the user item matrix data that we have discussed about, where we have tens of thousands of movies, of course, it can be analogous to tens of different thousands of dimensions in your vector space, right? And it's very hard to interpret also because you cannot imagine more than 3 dimensions in reality. And of course, you cannot go about wasting your resources and also causing inefficiency by having sparse data there, because most of the dimensions will have zeros there and does not hold any information at all, right? So linear algebra has got certain concepts which will help you extract the relevant portion from a large matrix so that you can work on much smaller matrix and much meaningful matrix there, thereby reducing the number of dimensions that you have. You had tens of thousands of movies or tens of number of dimensions, isn't it? So of course, because of addressing this sparsity issue, you are cutting down so many number of dimensions and you are confining to a much smaller number of dimensions now using certain concepts or certain techniques in linear algebra. And this area is called dimensionality reduction. And dimensionality reduction is also one such key area that we are going to discuss in this module. So there are various other techniques in linear algebra, not just dimensionality reductions. It can also help you perform data transformations. And there are also certain areas like matrix factorization, which relies upon linear algebra concepts. And we are going to discuss about each one of them. We have pretty much discussed about how you represent the data and what exactly is a vector, how you represent vector in a vector space or coordinate space. That is, every single vector that you have has got certain set of coordinates depending on the number of dimensions that you have, right? For instance, if you are having 3 different dimensions, then you have 3 different coordinates that a vector has got. The terminal point is determined completely on the values pertinent to three different coordinates that we have supplied. So every dimension here is nothing but your feature, and that's the key. And hence, in your data, you call all of these columns either as dimensions or features or independent variables. Let's also understand what independent variables are, but not now, maybe much later in this particular course. But let's understand that every single column can also be treated as dimension or feature from what we have understood in this session. Okay. In the subsequent session, we'll understand more about vectors, vector spaces, and what are the different operations that one can perform using vectors. All right. That's all in this particular session, and thanks for watching.